Thanks very much, ladies and gentlemen. Today's presentation is really come about from some research that we've been doing on two buildings and two projects in two different cities. One project was a multi-storey commercial office building in a temperate climate in the city of Sydney, and the other project was a master planning study, which was done in a tropical climate in Singapore. And when we did the two projects, we had to do it obviously for the client's benefit and to develop some reports and some data and generated from it. But it occurred to us, well, maybe there's an interesting data that we can get out of this by actually swapping the models that we had to do into the different climates. So we took the multi-storey commercial office building and we placed it into the tropical climate to see how it would perform. And then we would take the master planning study, which looked at passive features of different building shapes and orientation, and we put it into the temperate climate to see how it would perform. So hopefully we'd be able to get some data out of that, which would demonstrate give us some ballpark key figures on how a building can actually perform and what are the key factors that actually make a building perform. You're probably all familiar with this diagram here. It's a diagram that I remember seeing for the first time maybe about 10, 12 years ago. Developed initially, first time I saw it, by Klaus Daniels in one of his early books, and then of course again by Ken Yang. And it really talks about the preferred or the optimum orientation, the optimum building form of different types of buildings in different climates. And it makes a lot of sense. Having a round building in a cold climate means that regardless of where the sun is and coming up and going down, it's always getting sun into the building, providing warmth. And then, of course, if you look at the tropical climate, as you start moving to the lower latitudes, the sun is rising first thing in the morning, and it's directly hitting onto a building, and then going directly overhead. So then it's setting again in the west, and it's directly hitting the building. So having a very small facade on the east and the west has a less of an impact on your building, and it makes a lot of sense. And then, of course, the orientation of that building, just to make sure that you get the benefit of that. So it occurred to us, well, why don't we actually put this to the test and do some modelling to demonstrate what is the benefit that you're likely to get in today's buildings, where the facade is a lot better and also where the air conditioning systems are a lot more efficient. This is a view of the tops of buildings in Sydney, Australia. It's a great big picture, actually, and when you look at it, you can see the diverse range of different types of building shapes, and you ask yourself whether those buildings have been shaped because of any environmental reasons to provide more energy efficiency in the building or not. For example, down there, we've basically got an octagon. Here we have a square building, probably the 1.16 to 1 ratio, ideal for a temperate climate, facing north, which of course where the sun is in Sydney. This one, of course, large facade on the east and west, so of course you're getting that very strong east and west sun in the morning and in the afternoon. Not ideal, you would think. And then, of course, a few other ones which are located in different. This one's a northwesterly facade orientation. Another square one. That one's northeast. And of course, we've even got a round one, which is really nice. And not to mention that, we've also got two triangles as well. So when you look at it, I mean, you start questioning, well, what was the decision? Well, it's obvious that it's got nothing to do with the facade. It's got nothing to do with the environmental considerations of the building. It's probably got more to do with architectural whim. It's probably got more to do with the shape of the site and also how that building actually interrelates with other buildings around it as well. And views as well. Where are the views in the building? Where are they going to get the most amount of return for that net lettable area? But it's an interesting study in any case to see what influence any of those shapes will actually have on a building's performance. But of course, when you also look at the picture of a building which has got many different floor plates, when you think about it, if a building has got a facade on it, the larger the floor area as a percentage of the facade, as large as the floor area, the percentage of the facade becomes smaller and smaller. And so your facade will have a lower and lower impact on your building energy than you will for a smaller floor plate facade. And typically, the facade impact on that size, that part of the building, will be a larger proportion of the building energy than, of course, that one, than, of course, that one, and, of course, that one as well. And so your facade, influence of facade becomes diminishingly smaller as your building floor plate gets larger. And then, of course, there are the facades themselves. Typically, a lot of buildings have double glazed units, high performance double glazed units these days, curtain walling, U values of anywhere from 3 to 4, depending on whether you're looking at centre of glass or the whole frame. Solar heat gain coefficients of 0.18 to 0.2, visual light transmissions of 50% or so, sometimes a little bit smaller, depending on the floor plate and glare issues. And typically, if you look at the US dollar, about $750 to $850 a square metre for a typical type of high-performance double-glazed unit curtain wall facade. And then, of course, you start looking at the more complex types of facades, the double-glazed units with frits. Same sort of U value, maybe a little bit better on average as a shading coefficient. Visual light transmittance can be reduced down to 30 to 50, and of course, a little bit of an increase in the cost per square metre. There's the Oculux system, which again is a little bit more expensive, 40% visual light transmission, and of course, getting up to about 1,200 square metres, but a significantly increased solar heat gain coefficient reduction. And then, of course, there's the concept of having external glazing, external screen glazing, much better solar heat gain coefficients, higher on average visual light transmissions, but of course an increase in, or a similar cost per square metre facade as well. So the cost's starting to go up. And then we start getting into the very complex types of facades that you get in some buildings. The accessible double skin facade, where you access it from inside to clean the glass and the shading devices, etc. Again, the U value is 2.3 to 3, but the solar heat gain coefficient is down to 0.08 or 0.15. So that's only around about 8 to 15% of that solar heat gain actually getting into the building. And of course, you can get the visual light transmissions up to around about 60% in there without too much of a problem. But there's a cost premium to go there. You're going up to 1,400. And then, of course, there's the ventilated double skin facade as well, which is like the creme de la creme. You look there at the U value of about 3, but again, the shading heat coefficient comes down to 0.5. You can again increase the visual light transmission. And of course, when it gets too glary, the blinds can come down and such like. Again, an increase in cost up to about $1,700 a square metre. So the question's got to be asked, what benefit are we going to be getting from having a very costly facade from an energy perspective? And is it really an investment that is worth is going to pay back a dividend? And so we'll have a look at that a little bit later when we do the analysis. And then, of course, is the climates. If you look at the dry bulb temperature of both these two cities, they vary, as you can see. And, of course, the green being the tropical Singapore, very constant, about 25 degrees to 32 degrees most of the year. It doesn't change much. Usually it rains in the afternoon. That's Singapore's climate for you. But, of course, if you look at Sydney, it dips down in the winter time, which, as you expect, and, of course, the difference between that is that temperature difference, which gives you the opportunity of a bit of free cooling during the year, and when you don't need to run your chillers, etc. What is interesting, though, is on the right-hand side there, the temperature in Sydney can actually get up to 40 degrees. In fact, I've been there when it's 45 degrees, which is a lot hotter than Singapore. So you'd think that the peak load is probably significantly higher. But when we start looking at the actual energy in the air, this is the temperature in the air, it's not the energy that's in the air. When you look at energy in the air, we can look at wet bulb temperature, and wet bulb temperature is pretty close to your enthalpy of air. And you can see that the gap between Singapore and Sydney is widened. And that's because there's a lot more humidity in the air as well. But what is interesting is on the left-hand side in February, there's a point in time when the peak enthalpy of the air in Sydney is very similar to the peak enthalpy air of Singapore. So if you're designing an air conditioning system in both climates, the peak capacity of those systems would probably be pretty much the same. So assuming that your capacity is probably going to be about the same, what you're looking at as a difference then is going to be energy, and it's really the difference in energy is going to be that gap in the middle when it comes to outdoor air. So what we did, we ended up modelling this building here. This building is in Sydney. It's currently in the process of being topped out, designed by FJMT architects and being built by Grocon. It's an exemplary building. It's a world class. It's achieved a 6-star Green Star design, and it's going for its 6-star Green Star as built as we speak. It's achieved what we call a 5-star NABERS, which is the National Australian Building and Environmental Rating Scheme. And that system actually looks at you modelling a building, energy consumption, and then you've got to commit to that model result. And then at the end of the day, 12 months after the building's been built, you have to measure the metres to demonstrate you get the same target. And a lot of buildings in Australia do that, and they achieve it. And consequently, we've undertaken the modelling for this building and been able to determine how much energy efficiency or what energy consumption the building will actually consume. Typically, it's a chill water system. If you start with a facade, it's got a very high performance facade. We've got a visual light transmission on the northeast here of around about 55% with a shading coefficient of around about 0.26. On the west, east and north facade, and the north facade is actually quite a small facade down through here. The shading coefficient is down to about 0.23. So it's a very, very high performing facade building. Chill water air conditioning system with active chill beams on the perimeter and a low temperature VAV system in the centre of the core of the building. We've also got a boiler, and we've also got a couple of TriGeneration systems there to do a fuel swap. No wind turbines in the building. This is the model of the building. So we ended up modelling it in IES, and when we modelled the building, we modelled it right down to the last. We basically programmed the model as you would program a BMS system. So you were basically controlling every coil, every air handling unit, every fan to operate as the building would operate. From that, we were able to dissect the energy consumption of the building to see how it performs in different in the different spaces and climates. And this is some of the results that we ended up getting. You can see there in the tropical climate, the chillers actually contribute to 34% of the energy. Now, that's probably not surprising. The pumps of which the chillers are served by, 6%. The heat rejection, which is basically cooling tower, an additional 7%. So you can see that the cooling for this building in Singapore is contributing, is about 45% for just the cooling, before you get into the air handling of any air conditioning systems. The air handling fans are around about 10%. And then, of course, you get down to the smaller things like maybe a few package units for the security office or computer room or something like that. There's the auxiliary fans like toilet fans and car park fans. There's lifts are about 8% for this building, generally. And tenant lighting about 20%. Then when you look at the temperate climate, you can see that there's quite a shift in the cooling demand of this building. The chillers have gone down to 11%, which is understandable, because in Sydney, the climate allows you to operate your air on free cooling, outdoor air, for around about 55% of the year. The tenant lighting becomes more prominent, and the air handling units become more prominent as well. So then when you actually break that down to what proportion of the energy consumption of the total energy, which includes lights and everything else, is air conditioning. In the tropical climate, it's about 60%, and in the temperate climate, it's about 40%. Now, that's worth remembering, because when we start looking at some of the passive considerations and modelling of the building, that actually becomes important to consider. And, of course, that's the breakup of those different charts. So then when you actually look at the actual consumption rather than a percentage of the building, you can see here that a lot of the loads are fairly similar for both, which you would expect. Lifts is the same. Domestic hot water is a little bit different. You don't use much hot water in bathrooms in Singapore. Hydraulic pumps, miscellaneous loads, etc. You only start to see a bit of a difference when you go into your chillers and your chill pumps and your heat rejection plant and such like. Your air handling unit systems are fairly similar. So regardless of whether you're in Singapore or in Sydney, the air handling plant isn't much difference. But what is interesting is this, and that's the cooling energy. And so when you break up that cooling energy, you can start to see here that internal equipment doesn't make much difference, nor does internal lighting or internal occupancy. External conduction does. In Sydney, it's actually giving you a benefit because it's cold outside most of the year. Solar gain's quite small. But the big issue, or the big item that's making a big difference, is outside air, and that's made up of latent and sensible heat. So when we go to the effective form of orientation, we basically looked at all of those square, rectangular, and rectangular north-south and east-west, and we also looked at facade. And we modelled all of those, and with the facade, we used the ETTV calculation based on the green mark system, and we used a case where we had these values for a base case, and then we reduced the performance of them by about 50% to see what impact that would have. And in the end, we came up with a chart like this, and of course, this chart is in the paper that you'll be able to see. We basically had a building aspect ratio square, a rectangular 3:1, and a rectangular 1:3 with a long facade orientation, and then we had a facade ETTV of about 40, which is the green mark platinum. And that gave us some energy numbers. And what we've done is we've actually referred it all back to the 3,000 square metre model for a square. And you can see we've modelled a 3,000 square metre model, a 1,000 and a 500 square metre floor plate. And the reason to do that is to see what impact that size of floor plate actually has on your building. And then, of course, what is interesting here is that you can see that the difference is around about, for a 3,000 metre square floor plate, between a rectangular 1:3 and a square is around about 4.3%. It's quite small, isn't it? And then we looked at the increase in the ETTV. So we can see the difference between a 60 watts per square metre ETTV for the 3,000 is 102.3% against the 100%. So it's a difference of 2.3%. It's quite small. Of course, with the 500 square metre floor plate, it's 111.7 as opposed to 101.6. So you simply subtract one from the other to get the difference in percentage energy consumption difference. And then we did the same for the temperate climate to see what the difference is for each of those. And again, you're starting to see 1 or 2% or even here 2% differences. So it's not a huge amount of difference. So you start to see that facade and orientation isn't making a big impact on our energy consumption in the building. But what it does make an impact on is your peak demand. And this is your peak demand of your central plant, not even your perimeter plant. So your central plant, you're starting to have a look there at differences of around about, well, you're getting numbers of 143 against 130. So you're looking at 13, 14, 15% differences. And of course, that's one of the reasons we start to look at more high-performing facades, because that has an impact on reducing plant size, which has an impact on reducing increasing net lettable area and reducing cost as well. And then, of course, when you look at the charts here, you actually can see the difference there of a square against the rectangular and 3:1 or 1:3, and it's very small difference between each of those bars. But what is interesting, as you go from 500 to 1,000 to 3,000, you're getting that trend starting to go down, which means you're getting that law of diminishing returns. Similarly for form and orientation, similarly for facade performance. Here, this is actually the difference between a 40 and a 60 ETTV. So you're looking around about a 5% difference here for a 500 square metre building, and for a 3,000 square metre building, you're looking at around about a 2% difference. And what's interesting to this as well is that, and that's peak demand, is that you recall that air conditioning energy, which is what this difference is only 60% of the total energy of the building. So this is reduced even further when you start thinking about the total energy consumption of the building. And we did the same thing for the temperate climates as well. And so these, again, you can have a look through in the presentation. But similar sort of trend down as you start, your floor plate's getting big, but very small numbers, again, when it comes to form, facade orientation, and facade performance. And of course, in the temperate climate, the air conditioning is only 40% of the air conditioning, of the total energy. One of the other options that we've looked at too, one of the active things, is TriGeneration. It's very popular in some parts of the world, and it works basically by taking in gas, burning it in an engine, using the heat to drive an absorption chiller, and of course then using the electricity to provide in the building. And what we would normally do on a thermal system is you would size an air handling unit or TriGeneration system there, where you've got the number of annual hours against the capacity. So this TriGeneration system, which is doing, say, 14 watts per square metre, would operate for 2,000 hours. And then you could put another one in and another one in. And you would do the same for your TriGeneration system in Singapore, which, of course, would operate for longer and higher capacity. But, of course, in any commercial office building, you need not only thermal energy to get rid of, but you also need electricity as well. And, indeed, that red line is the electrical load in a building for the number of hours. So your TriGeneration system in any air conditioning, in any building, commercial office building, where you're not providing energy for plug load, is actually going to be restricted to that size. And when we did the analysis on TriGeneration, we actually found that because of the difference in the cleanliness of the energy within the two different cities, one uses gas turbines, one uses coal-burning power stations. In Sydney, you would get 11.5% reduction in greenhouse gas emissions, but in Singapore, you'd get probably something in the order of a 15% detriment. So it really doesn't, it doesn't pay to, there's no reason you would want to put in a TriGeneration system in that sort of building, in that sort of climate. And then, of course, photovoltaic arrays. I'm not going into wind turbines. I've got my own opinions on those. But with regard to photovoltaic arrays, it's naturally, as buildings get taller, the amount of floor area on the roof of a building to put in a photovoltaic array reduces proportionally. And if you start to do the calculations, it actually, as you start getting above 5 stories, you're well below 3% of your total building energy, and it sort of peters down to quite a small number. There's always the option to put in PV arrays on the face of a building, but of course, if you're in the tropics, you'll only see 50% of the day. And of course, as the sun moves away from the normal angle on a PV array, you're starting to lose efficiencies to the point where it becomes quite small. And so really for tall buildings, PV arrays don't provide too much benefit. So in summary, if we look at the passive influences of buildings, typically the impact of total energy on a tropical building is about less than 5%, but the impact on the peak power is between 14 and 17%. The orientation, total impact or the impact on total energy is actually less than 1%, but the impact on peak power is 1 to 3%. Now, the other thing to remember too, this doesn't look at the perimeter zone. This is the total energy of the building metered coming into the building at the meters, the electricity meters and the gas meters. And the facade, the impact on total energy is less than 4%, and the impact on the peak power for denigrating by 50% is between 3 and 7%, depending on the size of the building. And in the temperate, fairly similar numbers, less than 2% for form, for energy, orientation less than 1%, and facade less than 2.5%. Quite small numbers, but it does give you a bit of an impact or a bit of an idea of what you're playing with. So the active influences, TriGeneration, there's no benefit in Singapore. Photovoltaic arrays, less than 1% for buildings over 15 stories. And in the temperate climate, remembering it is a fuel swap, it actually uses more energy. So if your KPI is energy, it's not a good way to go. If it's a greenhouse gas emissions that you're trying to reduce, in some climates where they generate electricity with dirty fuel, it is a very valid way of looking at it. And what this actually suggests is that if we're looking for a low energy building, which is actually going to be clean energy, maybe we move away from trying to put PVs and and TriGeneration systems and wind turbines on buildings, and start looking at a precinct-wide system where you have photovoltaic arrays in areas which can feed into a grid which serves a precinct, where wind towers are actually located on headlands near the sea, where they're actually going to be very efficient in operation, and where you have district heating and cooling, which can be used to provide a larger amount of energy to the district. And the main energy influences, typically in a tropical climate, as expected, the cooling plant's the biggest, outdoor air latent load followed by sensible load, and then internal loads, which of course you don't have much control over except for the lighting, facade infiltration, and then followed by tenant lighting, air handling unit fans and lifts. And then in the temperate climate, you've got tenant lighting is what is the main influence. So if you can control your tenant lighting by reducing it from 12, 13 watts, 14 watts per square metre down to 3 or 4 using very low background and then of course task lighting, you can start to see significant back gains. Followed by air handling unit fans, and some of those concepts for reducing fan energy, like increasing your air handling unit so you can reduce the static. As you reduce the static in a fan, because it's operating for the 2,600 hours of an office building, you can make some significant roads into kilowatt hours. Okay, and then of course the cooling plant, followed by cooling plant, which is internal loads and solar gain, and then of course lifts is the next big challenge for engineers, is to reduce energy in lifts. So some of the strategies: daylighting. In the tropical climates, heat exchange is going to be a major area where you can reduce not only latent but also sensible energy consumption. There's also the concept of low temperature VAV, where rather than increasing your air volume first and then cooling it, you reduce your cooling, you reduce your temperature of your air into the space first, and then you start to increase more air. And the benefit of that is that you actually reduce your fan energy significantly, and you make your chillers work harder. And if you work your chillers harder, they're more efficient in this day and age. But of course, to do that, you will need things like swirl diffusers so you don't get cold air dropping on people's. And then, of course, you've also got the option of active chill beams or even passive chill beams, depending on the climate. So there are some of the, a bit of a summary of where the energy consumption is in a building, and hopefully it'll be a guide to architects and engineers. If you want to look for a low energy building, we need to look at where the energy is actually being used, and the big ticket players, which we can then hone in on, start making small percentages on big items. I hope that was of interest.